We move on from thinking about AX equal to B to starting to think about this concept of what's called eigenvalues and eigenvectors. This is a property of many matrices that are really important to not only find but characterize, allows us to characterize the system. So we're going to learn about eigenvalues and eigenvectors, and I always like to think about the fact that once you know the eigenvalues and eigenvectors of a matrix, you kind of know everything there is to know about that matrix and potential solutions that you might find when you come back to looking at AX equal to B. Again, I want to point out all the lectures are here at the website, so you can have in the link below this, there is a direct link to the website, and you can find more videos as well as lecture notes on this. So without further ado, we're going after eigenvalues and eigenvectors. So we've been spending a lot of time talking about AX equal to B, but now we're going to start talking about AX equals lambda x. So what does this mean? So we're looking at here a situation, right, when we have a matrix A multiplied by a vector, which gives us back a number, a scalar, and the original vector. So when we multiply by this matrix, we get back the same vector, but now with the scaling factor of lambda. So if lambda is bigger than 1, it takes this vector x and stretches it, makes it longer. If lambda is less than 1, then it takes this vector and it shortens it. So it's kind of an interesting idea, really, what this thing does for us, right? But it keeps the vector x in the same direction. Normally, when we think of AX equal to B, A acts on x, and then it produces a new vector b, which is generically in a different direction than x. But now these are very special directions, and what we're going to call these directions are the eigenvectors. So what are the vectors x, so that this property here holds? And when we start thinking about this number here that comes out, lambda, this is called an eigenvalue. So for each problem or each matrix A, we can try to find a set of eigenvectors and eigenvalues. In fact, we don't necessarily have just one vector. Generically, if we have an n by n matrix A, then we will have n distinct eigenvectors along with n eigenvalues. And there's lots of interesting things to be thinking about with this model here, because we want to think about what does the collection of these eigenvalues and eigenvectors mean? How does it help us in thinking about solving problems across engineering and physical sciences? So I'll give you one application area where this immediately comes into play, and that is linear differential equations. So differential equations model many of our physics-based systems, right? So we have some kind of quantity y that's evolving in time. dy dt tends to tell us how is this quantity changing over time, and most of our physics models and engineering models we use are calculus-based, and it's relationships among quantities that are changing in time or space. Here, we're just thinking about some quantity changing in time. So this could be, for instance, force equals mass times acceleration, which is acceleration is a second derivative of the position. And so we could always write it in this form here. So dy dt, and we're going to make a linear model, ay. So there's a matrix A, and y is there. And so most of differential equations, at least in an introductory course, really focus quite a bit of time on this model right here. And our number one solution technique is to basically assume exponentials as the solution. So here, we're just going to assume that all the time dependents have exponential behavior. And in fact, that's exactly what we do with linear systems. And we just plug this solution here, or this assumed solution form, right into the differential equation, which is here. Now what you'll notice is when I take the derivative, time only appears here in the exponent. And of course, differentiating exponentials is quite easy. All it does is gives you back the exponential and drops down a factor of lambda. So once we do that and plug that in, what you find is an eigenvalue problem. So immediately, for most differential equations that we study that are basic differential equations, immediately leads to an eigenvalue problem here. And this is an interesting concept because now what we're finding is that if I'm looking for solutions to differential equations, I have to solve the eigenvalue problem, and the collection of eigenvectors and eigenvalues are going to be essentially my solutions that I can add them together to form a general solution. So this is going to be this concept of linear superposition, but this is a linear model, and so of course superposition is going to hold there. And so you see that the basis solutions come directly from solving the eigenvalue eigenvector problem. So, and again, once you have them, then you're looking at, say, if I can get these eigenvalues and eigenvectors, I can just add them together to form a general solution to that problem. So the question then comes, how do you actually compute these eigenvalues and eigenvectors? And so we're going to come back to the model here, ax equals lambda, and notice here I multiplied by 1. So there's an I in here, the identity matrix. So ax equals lambda ix. And the reason I put the identity in there is because I'm going to do some manipulations now to sort of bring this into a form where we can start getting ourselves set up to solve this equations. So once I have this, I can actually move the right-hand side over, and what I find here, right, is ax equals lambda ix equals 0. And the reason I brought in the identity is because now I'm going to combine these two terms together on the left. So I have a, but notice that both are multiplied on the right by x. So in doing that, this is finally what we get here, which is a minus lambda ix equals 0. Essentially what this means is you take the matrix A and you subtract lambda from the diagonals. That's exactly what this model here tells you, and a minus lambda ix is equal to 0. So now this is a new matrix. A with lambda subtracted down the diagonal times x is equal to 0. So there's a couple options that can happen here, because again, I'm trying to solve for those lambdas and the x that would make sense in this problem. And what's interesting here, normally we always think about the fact that if I want to solve an ax equal to b problem, so in other words find an inverse of a matrix, I want to make sure that the determinant is not 0. But in this case, we actually want the determinant to be 0. And here's why. Because option 1, this matrix here, the determinant is not 0, which means I could invert it. Normally this is a good thing for us to solving an ax equal to b problem. And so if I take this option 1 and I say the determinant is 0, that means that matrix A minus lambda I has an inverse. So great, so I can get the solution, which is x is equal to the inverse of that matrix, but on the right hand side I had 0. So when I invert this and I multiply by 0, then what I find is just the trivial solution, x equals 0, right? That's exactly what this multiplication gives you, is the only solution is the trivial solution. And so I don't want the trivial solution. What I'd like to do is find some other solution that is certainly not 0. I could have told you 0 was the solution to this all the way back here, where you just simply plug in 0 here, 0 here. But what we're really looking for is something that's not 0, some non-trivial solution that characterizes the behavior or the solutions of this matrix in A. So I'm going to go with option 2. The only other possibility is that the determinant is 0. And then we're going to see what the consequence of that is. So what we're going to try to do is enforce that the determinant is 0. So if I do that, I can no longer invert that matrix. But now I have the potential for solutions, and I'm going to show you how this all works out in a moment. But how I'm going to enforce that is by picking the lambdas. And in fact, lambda is just some scalar, or a set of scalars that I can pick. And I'm going to pick them so that the determinant is exactly 0. That is how I'm going to determine the eigenvalues. So let's do it for a simple example. I'm going to give you a matrix A. Here it is. It's 2 by 2, very simple matrix. And what we're going to do is we're going to go through this process of looking at the eigenvalue problem and setting that determinant to 0 and seeing what it means for us in terms of getting solutions or eigenvalues and eigenvectors for this problem. So first things first, what I do is I take my matrix, I subtract minus lambda times identity, there it is. And so all this is going to do is subtract lambda off the diagonals here, and that's what I get here. So this is my new matrix. This matrix times x is equal to 0. Okay? And again, if this has an inverse, then the only solution is 0. So what I'm going to try to do is make the determinant of this matrix here exactly equal to 0. So this is what this calculation does here. The determinant of a 2 by 2 can be very easily computed as you take the diagonals and you multiply them together and you subtract the multiplication of the off diagonals. So when you do that, you get 1 minus lambda times 5 minus lambda, and then a minus 3, which is plus 3. Write that all out. Here's a quadratic equation, and then you can factor it into this form here. And in fact, generically, if you had an n by n system of equation, you would get a polynomial of degree n here instead of a quadratic equation. Since we're working with a 2 by 2 system, what we end up getting out of this is a quadratic formula. So in other words, a second degree polynomial. And what we have to do is to make the determinant 0 is we actually have a root solving problem here. And there it is. And in fact, this one is easy to do. There are two possible eigenvalues. Lambda equals 2 or lambda equals 4. Both make that determinant 0, which means gives me the potential of having a non-zero solution. So how do I get to these solutions? Well, let me come back one step and just look here at this equation here. This equation still has to hold. And so I'm going to use this equation here where I've subtracted lambda off the diagonal and see if I put in now these two values of lambda that I've learned, lambda equals 2 or lambda equals 4, what does it imply for this equation right there? Okay, so I'm going to do one at a time. We'll start off with lambda equals 2 and then do lambda equals 4. So let's talk about lambda equals 2. So here's lambda equals 2, here's the calculation. I just go back to that system and I put in 2 where the eigenvalue should have been, where the lambda was. But now I know the lambda value, or at least two lambda values, and I'm going to use the first one, lambda equals 2, and then I'm going to go ahead and put it into here. What you end up with when you put it into here is this equation here. But notice the first and the second equations actually are exactly the same. Minus 1 times x1, which is the first component of x, plus 3x2, which is the second component of x, is equal to 0. So I can write that here as this equation here. So this is an important equation because it gives you a relationship between the first component of the vector and the second component of the vector. And notice it's underdetermined. So it doesn't specify what x1 and x2 have to be. It just specifies that they are related in this way right here. Okay? And so what we're going to do is we could do a couple things. But the easiest choice, I can pick x2, for instance, to be 1. And if x2 is 1, it's going to enforce that x1 is 3. So for instance, there. That is an eigenvector to the system. Okay? Now, of course, there's an infinite number of choices here. I've picked this eigenvector. But the fact of the matter is, you may pick your own eigenvector. So to make them compatible, oftentimes what happens is people will pick this eigenvector like this and then normalize it to unit length. And then that way, your pick of an eigenvector would match my pick of an eigenvector up to a sign change, okay? So that's how we would get an eigenvector. And it's in this direction, 3, 1, okay? So this is interesting, right? So the eigenvalue lambda equals 2 gives me a very specific direction along that whole line, which is, 3, 1, any vector along that line that gets multiplied by a stays on that line, which is the eigenvector line. Let's go to the second eigenvalue, lambda equals 4. And so lambda equals 4, we're going to plug that in. Here it is. You're just going to put the 4 into there now. And now here are your two equations. Notice that they're actually, again, the same. You get negative 3x1 plus 3x1, which is the same as the second equation, which is negative x1 plus x2 is equal. In other words, I can just take that first equation, divide by 3, and they're exactly the same equation. And generically, when you have an n by n system, if you have n distinct roots of the polynomials, in other words, n distinct eigenvalues, this actually will always come out to be that these are degenerate in the sense that you have the same equations in the rows. Okay? There are times when you have double roots of eigenvalues or triple roots. In other words, you can have that kind of structure, in which case this equation can become a little bit more interesting in those cases. But right now we're just going to think about cases where each eigenvalue is simple. In other words, there's only a single root for each. So this one here is the end equation, negative x1 plus x2 is equal to 0. Again, underdetermined. And again, gives me a lot of freedom about how to choose this. So I could pick x2 to be 1. And if I pick that to be 1 here, then x1 is 1. And this is a second eigenvector. So this eigenvector is in the direction 1, 1. It's different than the first eigenvector's direction. And this one is associated with the eigenvalue lambda equals 4. So a generic solution to ax equal to b, by the way, I could do this as a linear superposition of the two eigenvalue pairs that I have here, which is the lambda 2, which is in the direction 3, 1, plus the eigenvalue with lambda equals 4 in the direction 1, 1. These directions are really important because what they're trying to tell us, what the eigenvalues and eigenvectors tell us, is these really important directions on which solutions sit. And we're going to really dig down on this as we go forward and give examples of this. But eigenvalues and eigenvectors, in some sense, are the right coordinate system to be using for a given matrix A. This is about a coordinate system. This is one of the coordinates that you're going to have here. This one here, and the other eigenvector is the other coordinates. All the action can be thought about things that collapse down onto the eigenvector coordinate system. So you can represent anything in this matrix as being things that happen in these eigendirections. By the way, there's a lot of different ways you might want to think about getting your eigenvalues out and sorting them. Remember, I just did a 2 by 2 example, but generically we're going to be looking at n by n system, so very large system of equations, right? So A is going to be large. We're going to have a large collection of eigenvalues and eigenvectors. And so one of the things that we want to do here is figure out how do we want to sort our results. And this gives you a list of some of the options available to you in MATLAB or Python to sorting the eigenvalues. You can say LM, which is the largest magnitude eigenvalues. And magnitude, you know, these eigenvalues can be imaginary and complex. And so largest magnitude takes into account both the real and imaginary parts of those eigenvalues. Okay? You can also look at the smallest magnitude, or the largest algebraic, smallest algebraic, largest real part, smallest real part, largest imaginary, smallest imaginary, or both ends, which means you can look at sort of the extremes, the largest and the smallest. So there's a lot of options about sorting these, because if you have a large matrix, you may only be interested in the dominant eigenvalues. What do I mean by dominant? Potentially those with the largest magnitude. If I give you a million by a million matrix, it's very rare that you're going to want all million eigenvectors to look at, or eigenvalues, but you might want to see what do the top 10 look like. And we'll show this in the next lecture when we think about this application of eigenvalues and eigenvectors to what is called eigenfaces. So, some more thoughts on this in terms of bringing all of this together. I want to collect all the eigenvalues and eigenvectors of a system together into a very compact form and representation, which is given by here. This is a very important equation. What it tells you is here's the matrix S, A, and it's multiplied by S. And what S is the collection of all the eigenvectors, right? So I've already shown you in this one example, which is a 2 by 2, that there's 2 eigenvectors. So I could write down an eigenvalue problem for each one of those eigenvectors, or I can bring them all together in this compact representation here, which is this notation here, okay? So S is the set of all the eigenvectors, and each eigenvector is a column vector of size n, if A is n by n. So I have all these eigenvectors, there's n of them, and then so I take A and multiply by S, and what I get back is S times this capital lambda matrix, And the capital lambda matrix has the eigenvalues down the diagonal. That's what this represents here. So it's 0 everywhere else, and just down the diagonal are the eigenvalues. So this, it doesn't take much to convince yourself that if you do column by column multiplication against each eigenvector, you end up with the eigenvalue problem for each one of those eigenvectors, which satisfies its own individual eigenvalue problem for lambda 1, and then lambda 2, and then lambda 3, all the way to lambda n. But the nice representation here is this is the full collection. And we can use this for a lot of different applications. We'll want to know this because what ultimately this allows us to do is take a matrix A and do a decomposition into a new coordinate system where S, or the columns of S, which are the eigenvectors, are the new coordinates that we're going to be working with. So this is an important piece of information because it's going to allow us to solve a lot of problems once we understand the structure of this decomposition in terms of eigenvectors and eigenvalues. The only thing I'm going to highlight here is an application where we can use this decomposition in a very, we can exploit the properties of this in a very nice way for doing computations, which can be very expensive, which is matrix, if I do some kind of matrix power, something like if I want to try to evaluate a to the nth power where m is large. This is a very expensive computation to just repeat multiplication by a over and over and over again, especially for large matrices. And in fact, this often comes up when doing time-stepping algorithms for large spatial temporal systems where you want to advance the solution into the future in time by multiplying by some matrix A which approximates the time dynamics of the system. So oftentimes you have to evaluate some very large matrix exponentiated to a very high power. So this is very expensive computationally. However, eigenvalues and eigenvectors allow us to do this computation in a very efficient way. So let me show you how this is done. I can take the fact that AS equals S diagonal matrix lambda and just multiply on the right side both by S inverse. Okay? The eigenvectors are in fact linearly independent, so I can find an inverse. And so the matrix A has this very important decomposition. Here it is. And what you actually have is the matrix S, the diagonal S inverse. So this here is really a very nice representation of a decomposition of the matrix A into its eigencoordinate system. The beauty of it is A, which is a full matrix, decomposes into this new coordinate system which is diagonalized. In other words, in the new coordinate system, once I've moved into my eigenvector coordinate system, I'm sitting in this direction, along these directions where it's diagonal behavior. This is really critical for many applications in differential equations as well as even computations that I'm going to show you here. Because once you have it in this diagonal coordinate system, look at some of the things that can happen for you. So let's go ahead and consider A squared. In other words, take a matrix and square it. So a matrix A in this decomposition is given by here. So I take A, multiply by A. But notice what you have once you've done this decomposition. In the middle, you have S inverse times S. These are multiplying each other, so this becomes identity, and then you end up with this being just now S, the lambda squared S inverse. So the squared piece gets picked up onto the lambda matrix. And in fact, if you did this m times, the matrix A to the m looks like this here. So it looks like what you've done is you just traded out multiplication of a matrix m times by a different matrix m times. But that lambda matrix is diagonal, and that makes all the difference because computing this is very cheap, inexpensive, and trivial. In fact, here it is. So if you want to multiply this matrix over and over again, all you have to do, you can do it by hand, just taking each one of the eigenvalues, raise it to the nth power. It's a very simple calculation. And so now what I have is a very efficient way to compute this, which then allows me, once I've computed this, I just multiply it on the left by S, on the right by S negative inverse, and I have a representation of that matrix to the nth power. So this is a really important computational trick when you're working with large matrices that you have to multiply by each other over and over again. And remember, this is all about scientific computing, and so I've just shown you how you can use eigenvalues and eigenvectors to your advantage in a computational setting so that you can, do a computation like this much more efficiently than if you were to just put it in a loop and multiply some large matrix over and over and over again. Good. So that's some of the power of eigenvalues and eigenvectors. I do want to hit one last thing at the end of this lecture, which is very important, which is this concept of what's called solvability. So I want to take ax equal to b again. This is ultimately what we're after throughout this course, right? And I want to start talking about the conditions under which you can get a solution for this. Normally we just simply say, well, if the determinant of a is not 0, then I just get a solution. But there's actually something a little more subtle here to be thinking about. Because it could be, in fact, that this is singular, a is singular, the determinant is 0, but you still might be able to achieve a solution because, in fact, it could be that b is still in the range of the operator a. So how do you actually, in a more rigorous way, determine solvability conditions for this? And this is what's going to be called the Fredholm-Alternative Theorem. What we're going to consider is the adjoint of the matrix A times y equals 0. So this is going to be a second equation we consider. So this is y is going to, if this is equal to 0, y is the null space of that adjoint operator. And I'm going to think about this operator, and I'm going to think about this vector y, because if there is a non-trivial vector y, check out what happens here for understanding the solvability. So I can take ax equal to b, and I've just written it here, and I've just dotted it on both sides by y. So I take my original equation, and I multiply both sides by y. And by the way, one of the things that I want to first highlight is the definition of this adjoint, which is if I have y dotted with ax, the definition of that adjoint is that now a transpose y is dot x. So this is the definition of the adjoint. So before we get back to x equal to b, just keep this in mind. This is its definition. Therefore, you can start thinking about, well, if I did this and go back to the original ax equal to b problem, this ax here is equal to b, so I have on this side y dot b. This is y adjoint, a adjoint y, but that's equal to 0 because that's how I defined it. So this is 0 dot vector x, so this is 0. So ultimately you end up with this condition here, that y dot b is equal to 0. In other words, y, which is the null space of the adjoint, has to be orthogonal to b for there to be a solution. And if that's the case, you can find the solution. What it tells you is that b is in the range of the matrix A. And so that is a very generic condition. We tend not to talk about this, but it's one of the most important things that really needs to be discussed when you're thinking about solving ax equals to b. Fredholm alternative has to be solved. By the way, an interesting observation is what happens if the only vector that actually, there's no vector that spans the null space, that y is in fact the only way to satisfy this, y equals 0. So if you put y equals 0, that means you automatically have solvability. It doesn't matter what b is, because if this is 0 dot b, then you get 0, so it has a solution. So if there is no null space to that adjoint operator, then you can satisfy this, the ax equal to b. So this is a nice condition for you just to be aware of when we think about solving x equal to b broadly. Okay, that wraps it up for eigenvalues, eigenvectors. Again, you can find more information at the website here. Just click the link below. You get more lectures, the notes, everything else, and as well as code. And again, these eigenvalues, eigenvectors, such an important concept to be developing as we start thinking about solving realistic problems. Again, I want to couch this in the language of coordinate systems. What eigenvalues and eigenvectors really are allowing you to do is move into a new coordinate system which has some very nice properties for us to be taking advantage of in modeling systems broadly modeling systems. In fact, we'll show that in the next lecture when we consider how to think about what are called eigenfaces. So we're going to think about these matrices just being data and what we can do with eigenvectors and eigenvalues.